For this project, we are tasked to develop a plant for producing methanol under the CFB 1043 Principle of Chemical Engineering and CFB 1053 Chemical Engineering Fluid Mechanics.
Hi, my name is Aiden Chayu Chuan.
Hi, I'm Felicia Shatrina.
Hello, my name is Aaron Muazzam Fitri bin Hassan.
Hello, my name is Bruna Tiasfir.
In this video, we will talk about Chapter 1A, Introduction Principle of Chemical Engineering, Chapter 1B, Introduction Chemical Engineering Fluid Mechanics, Chapter 2, CFB 1043 Principle of Chemical Engineering, Chapter 3, CFB 1053 Chemical Engineering Fluid Mechanics, Chapter 4, Conclusion, References, and lastly, Appendixes.
Now I'm gonna talk about the introduction of principle of chemical engineering. Global warming is a major concern driven by carbon dioxide emissions. A producing solution is producing methanol from carbon dioxide and green hydrogen using air capture. Methanol is a clean, sustainable fuel to green productions. Is still less efficient than fossil-based methods. Most methanol systems use copper, zinc oxide, and aluminum oxide catalysis at 200 to 300 degrees and 20 to 100 bars, similar to carbon dioxide-based process at about 76 bars. Now I'm gonna give the introduction of chemical engineering fluids mechanics. Industrial methanol is produced from synthesis gas, carbon monoxide and hydrogen, or by hydrogenating carbon dioxide and hydrogen. After purification, the liquid methanol is transferred from the final processing unit to storage. This design focuses on the piping system for safe, efficient, and reliable transport of the volatile fluid. For analysis, a standard plant capacity of 1000 mTPD is used as a typical large-scale benchmark.
Now I'll be explaining the process flow. So firstly, the carbon dioxide will be fed into multiple compressor units labeled as COMP1, COMP2, COMP3, and COMP4 to gradually increase the pressure of CO2 gas. We will increase the gas of the pressure up to 76 bars. And not only that, heat exchangers is placed in between every compressor, which will then heat up the CO2 gas up to 300 degrees Celsius to be ready to enter the mixer, which will then be mixed with hydrogen gas, which is compressed at COMP5 up to 76 bars also. The compressed and heated CO2 gas and H2 gas will be mixed at the mixer together with the recycled gas from the previous batch to ensure a homogeneous mixture before going in through the chemical reaction. The homogeneous mixture will then react with each other to form syngas at the reactor labeled as R1 with iron acting as its catalyst. And then the syngas will be flowed into the second reactor labeled as R2 to undergo synthesis and produce liquid mixture of methanol and water. The product from R2 will then be transferred to a separator to separate the liquid mixture from the unreacted gas mixture. And then about 5% of the gas mixture will then be purged and the rest will be recycled again. On the other hand, the liquid mixture will then proceed to be fed into the distillation column D1 and D2 for purification of our methanol.
For the non-reactive unit, so if the mass and molar flow rate of the inlet stream of CO2 and saturated steam as the value stated in the slide here, and also by assuming that the inlet temperature of CO2 and H2O are 100 degrees Celsius and 300 degrees Celsius respectively. So the picture shows the diagram for the heat exchanger. So our assumption here that the efficiency of the heat exchanger is 100%. Second, the gas behaves ideally. Third one, no heat loss to the surrounding. And four, the outlet temperature of the saturated steam is 35 degrees Celsius. For the mass balance, from the value given, we need to calculate the mass flow rate for the saturated steam. So by assuming that the value of the molar flow rate of the saturated steam as 1000 mole per hour, we can change it into mass flow rate by multiplying with the molar mass, and then can get the mass flow rate here. So and for the molar flow rate for the carbon dioxide stream, we can divide it by the molar flow rate to get the value here. Now for the energy balance. So for calculating the specific enthalpy of CO2, we are integrating from 100 degrees Celsius as our reference state to 300 degrees Celsius, the temperature that we are heating it to. So we're getting the value from the reference tables, and we can get the value as stated here. And for the specific enthalpy of the saturated steam, we can get also from the table, and we get those two values here. Now we're calculating the rate of heat. So we are calculating the sum of the outlet minus the inlet. So from the reference state, we can cancel a few integrations to make the calculation more simple. So we are calculating we put the values as for the outlet of the CO2 stream and the inlet minus the inlet of the saturated steam, and we can get the value as this value. And this value is the amount of heat energy that is required for us to heat the CO2 gas from 100 degrees Celsius to 300 degrees Celsius.
As for the reactive unit, the mass flow rate of the inlet is 3,419.83 kilograms per hour, and also the temperature and the pressure of the product is 350 degrees Celsius and 76 bar respectively. And the assumptions that we made for the calculations are every unit performs ideally in terms of all mass in equals to all mass out. Next, molar fraction is the same as the stoichiometric ratio, as well as the gases behave ideally. To calculate the mass balance for the reactive unit, first we have to calculate the molar weights for the inlet and the outlet. So firstly, for the outlet, we added the molar weights of carbon dioxide, hydrogen gas, methanol, and water because those four components are present as products, while for the inlet, it is only the molar weights of carbon dioxide and hydrogen gas. The total molar weight calculated will then be used in the formula below, which is the mass flow rate of a component equals to the total mass flow rate times the molar weight of the component over the total molar weight. Here we have all of the calculations of the mass flow rates for the inlet and the outlet. So from the calculations here, it is shown that the mass flow rate of the carbon dioxide in is 3009.532 kilograms per hour, and the hydrogen gas is 205.149 kilograms per hour. Well, for the outlets, we have methanol with the mass flow rate of 1095.166 kg per hour, hydrogen gas with 205.087 kilograms per hour, CO2 gas at the outlet which has 1504.315 kilogram per hour of mass flow rate, and lastly we have 615.262 kilograms per hour for the mass flow rate of water. As for the energy balance, the first step is to calculate the rate of enthalpy change. So to do that, we need to first set our reference states. I have set the reference states for carbon dioxide as gas state 25 degrees Celsius 1 bar, hydrogen gas as gas state 25 degrees Celsius at 1 bar as well. Well, for methanol, it is gas state 350 degrees Celsius at 76 bars. And lastly, water at liquid state 25 degrees Celsius 1 bar. After identifying my reference state, I then proceed to calculation for the rate of enthalpy change for the carbon dioxide at the inlet. So to do that, I first calculated the rate of enthalpy change when I changed the pressure from 1 bar to 76 bars, and then I calculate the rate of enthalpy change when I increase the temperature from 25 degrees Celsius to 300 degrees Celsius. And to find the overall rate of enthalpy change for carbon dioxide at the inlet, I summarized those two values and I got 186,196.265 kilojoules per mole. I then do the same thing for the hydrogen gas at the inlet and I got 170,233.962 kilojoules per mole. And then for my water at the outlet, I referred to the table B8 to get the value of when I increase the temperature from 25 degrees Celsius to 350 degrees Celsius, and then I did again the rate of enthalpy change calculations for when I increase the pressure from 1 bar to 76 bars, and then I sum up those two values to get 148.189 kilojoules per mole. I then do the same thing for the H2 out as well as the CO2 out to get 170,235.425 kilojoules per mole for hydrogen outlet and 186,198.653 kilojoules per mole for the carbon dioxide out, while my methanol remains 0. And this is because the reference state condition that is set for the methanol is the same conditions as the methanol at the outlet. Then I use the formula the molar flow rate of a component equals to the mass flow rate of a component divided by its molar weight to find the molar flow rates for every single component at the inlet and at the outlet. And from the calculations, I got that the molar flow rate of the hydrogen gas at the inlet is 205.149 mole per hour, while for the carbon dioxide it is 68.383 mole per hour, and the methanol at the outlet has 34.181 mole per hour as its molar flow rate, while the water is 34.181 mole per hour, and the carbon dioxide is also 34.181 mole per hour, And lastly, the hydrogen gas at the outlet is 146.359 mole per hour. Furthermore, I calculated the standard heat of reaction, which equals to the summation of the molar flow rate of the outlet times with the standard heat of formation at the outlet minus the summation of the molar flow rate of the inlet times the heat of formation of the components at the inlet. And then I got the value of negative 28,450.9849 kilojoules per hour. Moving forward, I calculated the extent of the reaction with the formula. The extent of reaction equals to the number of mole at the outlet minus the number of mole of the inlet over the number of mole of the stoichiometric. And then I got the value 51.303. And lastly, by using the formula, the rate of enthalpy equals to the extent of reaction times the heat of the reaction plus the summation of the molar flow rate out and the rate of enthalpy change of the outlet minus the summation of the molar flow rate of the inlet times the rate of enthalpy of the inlet, I can get my rate of enthalpy, which will have the value of negative 17830,599.17 kilojoules per hour. And by following the equation, the rate of enthalpy change plus the rate of kinetic energy plus the rate of potential energy equals to the rate of quantity of heat plus the rate of work. I can derive to get the formula the rate of enthalpy change equals to the rate of quantity of heat. Hence, I can equate these two to get the quantity of heat released from the reaction, which is also negative 17830,599.17 kilojoules per hour.
Assumption 1. Production capacity. The plant production capacity is assumed to be 1000 mtpd of pure liquid methanol. The physical properties and fluid dynamic calculations are highly dependent on operating temperature and pressure. Since the methanol has undergone purification and cooling, it is reasonable to assume it is handled at near ambient conditions, which minimizes thermal stresses on the piping and facilitates atmospheric storage. Assumption 2. Transport temperature. The transport temperature is defined as 25 Celsius. Assumption 3 and 4. Pressure conditions. The salting point pressure at the final processing unit outlet, such drum, is assumed to be slightly above atmospheric, approximately 1.5 bar. The final destination pressure at the atmospheric storage tank inlet is defined as 1 atm equals to 101.325 kilopascal. Calculation of methanol flow rate. The design flow rate is derived directly from the mass production capacity using standard time conversion factors. The mass flow rate calculation is 1000 mt per day times 1000 kg per 1 mt times 1 day per 86,400 seconds equals to 11.574 kg per second. The volumetric flow rate requires the liquid density. Using the density established, the required volumetric flow rate is 11.574 kg per second divided by 786.6 kg per meter cube equals to 0.01471 meter cube per second. Physical and transport properties of liquid methanol. The accurate estimation of pressure drop and pump requirements hinges on reliable physical property data for the fluid at a design temperature. Key properties for liquid methanol at 25 Celsius were compiled from established sources. Density is 786.6 kg per meter cube. Dynamic viscosity 5.93 times 10 to the power of negative 4 pascal second. Vapor pressure 12.53 kilopascal. Boiling point at 1 atm 64.6 degrees Celsius. A critical consideration in the fluid mechanics design is methanol's high volatility relative to common industrial fluids like water. For low boiling point of 64.6 degrees Celsius and a substantial vapor pressure of 12.53 kilopascal at the operating temperature of 25 degrees Celsius, methanol presents significant risk of vaporization flushing if the local pressure drops below this vapor pressure. This necessitates a stringent analysis of the net positive suction head available to prevent cavitation in the pump, which could lead to severe mechanical damage and operational failure. Furthermore, methanol's low flash point, torque suchness, and wide flammability limits mandate a completely closed and robust piping system designed to ensure safety and environmental protection. Selection and justification of piping material. The selection of pipe material must satisfy chemical compatibility, safety, and regulatory requirements. Material selection justification. Given that methanol is a conductive polar solvent that can increase governing and dissimulate metal corrosion, particularly if trace acidic impurities are present, the use of standard carbon steel is often restricted to less critical or lower purity surfaces. To maintain product purity and ensure long-term integrity, stainless steel type 316 is selected. This material offers excellent corrosion resistance and is suitable for handling bulk chemicals like methanol. Assumption for pipe specification. The piping is specified as stainless steel 316, Schedule 40S. Determination of optimal pipe diameter. The design of the pipe diameter is a balance between capital cost, favoring smaller diameter, and operating costs, favoring larger diameter to reduce friction loss and pump power. For non-viscous, water-like chemical liquids without entrate solids, an ideal flow velocity range of 1.0 to 2.0 meter per second is widely accepted in the industry. Assumption for target velocity. A target velocity of 1.5 meter per second is adopted for the transfer line. Based on the calculated volumetric flow rate, Q equals to 0.01471 meter cube per second, the required internal cross-sectional area and corresponding diameter were calculated, yielding a required diameter of approximately 0.1118 meter. Consulting standard pipe tables, the nearest common size is chosen. Selected pipe specification, nominal pipe size 4 inch, Schedule 40S. The internal diameter for NPS4 SCH40S pipe is 0.1023 meter. The resulting actual flow velocity is 0.01471 meter cube per second divided by pi divided by 4 times with 0.1023 meter square equals to 1.787 meter per second. This actual velocity is within the acceptable design range. Detailed piping layout and component specification. To quantify the pressure drop, the geometric configuration and component list of the pipeline must be defined. The system is divided into a suction side, such drum to pump P101, and a discharge side, pump P101 to storage tank. Piping layout assumptions. Total straight pipe length 350 meter. Justification, representative inter-unit distance. Pump placement 2 meter below liquid surface. Maximize NPSH due to volatile fluid. Total static lift. Discharge head Z2 minus Z pump 20 meter. Justification, typical height difference between grate and tank inlet. Pipe internal diameter 0.1023 meter. Justification, NPS4 SCH40S SS316. Absolute roughness 4.5 times 10 to the power negative 5 meter. Justification, typical value for new commercial stainless steel. Resistance contributed by fittings minor losses is defined using dimensionless resistance coefficients, K values, to simplify calculations for turbulent flow. This table shows defined fittings and minor loss coefficients. Fittings type, pipe entrance, surge drum outlet. Quantity needed is 1, K value 0.5, total key 0.5. Pipe exit tank inlet, quantity 1, K value 1.0, total key 1.0. Standard 90 degrees elbows, quantity 12, K value 0.80, total key 9.6. Gate valve fully open, quantity 2, K value 0.19, total key 0.38. Globe valve for flow control, needed is 1, K value 10.0, total key 10.0. T, flow through branch, quantity 2, K value 0.80, total key 1.6. Swing check valve, discharge, quantity 1, key value 2.0, total key 2.0. Total sum of key values is 20. while the total K is 25.08. Theoretical framework. The total frictional pressure drop across the piping system is derived from the total head loss, which incorporates major losses due to friction along the straight pipe sections and minor losses due to flow disturbance from fittings and valves. The fundamental equations utilized are the Darcy-Weisbach equations. First, frictional head loss, major losses. Second, fittings head loss, minor losses, where F is the Darcy friction factor, L is the pipe length, D is the internal diameter, V is the actual velocity, G is the acceleration due to gravity, just 9.81 meter per second square, and K is the sum of resistance coefficients. Calculation of Reynolds number and friction factor. The Reynolds number dictates the flow regime and governs the method used for calculating the friction factor, which is 786.6 kg per meter cube times with 1.787 meter per second times with 0.1023 meter divided by 5.93 times 10 to the power of negative 4 Pascal second equals to 244,000. Since Reynolds number is 244,000, the flow is highly turbulent because Reynolds number is more than 4,000. For turbulent flow in rough pipes, the friction factor depends on both Reynolds number and the relative roughness. The selected SS316 pipe has an absolute roughness of 4.5 times 10 to the power of negative 5 meter, leading to a relative roughness, which is 4.5 times 10 to the power of negative 5 meter divided by 0.1023 meter equals to 0.00044. The friction factor is determined using the Colebrook-White equation, which is negative 2.0 times with log 10 times with relative roughness divided by 3.7 plus 2.51 divided by Reynolds number times with F to the power of 1 over 2. Solving this equation iteratively for the calculated Reynolds number and relative roughness yields a Darcy friction factor of approximately 0.0199. This calculation confirms that because the Reynolds number is high, the friction factor is primarily governed by the relative roughness rather than vicious effects. This emphasizes the importance of selecting an accurate absolute roughness value for the pipe material. As slight changes in absolute roughness value in the turbulent regime can have a disproportionate effect on the final frictional head loss and subsequent required pump power. Calculation of total head loss and pressure drop using the calculated velocity V equals to 1.787 meter per second, internal diameter D equals to 0.1023 meter, the friction factor F equals to 0.0199, and the gravitational constant G equals to 9.81 meter per second square. Measure losses, friction head loss, based on the total straight pipe length of 350 meter. Then the minor losses, fittings and valves, using the total sum of key values. K equals to 25.08. So 25.08 times with 1.787 meter per second square divided by 2 times 9.81 meter per second square equals to 4.08 meter. The high contribution from minor losses, 4.08 meter, relative to major losses, 10.66 meter, highlights the significant resistance imposed by specific components, particularly the mandated globe valve, high K, and the check valve, which are often necessary for system control and safety, but are hydraulically restrictive. The corresponding pressure drop is 786.6 kg per meter cube times with 9.81 meter per second square times with 4.08 meter equals to 31,390 Pascal equals to 31.39 kilopascal. Summary of total pressure drop. The total head loss and total pressure drop due to friction and local resistance are summarized below. In this table, summary of pressure drops across all pipelines. Loss type, major loss friction. The calculated head loss is 10.66 while the calculated pressure is 82.31. Justification: Darcy-Weisbach equation F equals to 0.0199. Loss type: minor loss, which is for fittings and valves. The calculated head loss is 4.08. Calculated pressure is 31.39. Justification: summation of key values, K equals to 25.08. So the total friction loss equals to 14.74 for the calculation head loss and equals to 113.70 for the calculated pressure. Justification: summation of major and minor losses. And this is our piping layout. Application of fluid mechanics principles for product transfer. The strategy for delivering the final methanol product relies on the principles governed by the mechanical energy balance (MEB), derived from Bernoulli's equation, applied between the product system, point 1 pump suction, and the storage tank inlet, point 2 pump discharge. The MEB, expressed in terms of head meters of fluid, determines the energy input required from the pump, known as the total dynamic head, TDH. The TDH calculation simplifies to TDH equals to H pump equals to V2 minus V1 divided by density G plus Z2 minus Z1 plus V2 squared minus V1 squared divided by 2G plus HL total. For this system, pressure head term, assuming P1 surge drum and P2 storage tank are both open to ordinary atmospheric pressure, this term is effectively zero. Velocity head term, since the pipe diameter is constant, d1 equals to d2 equals to 0.1023 meter, v1 equals to v2, making this term negligible. Third, static head term, z2 minus z1 equals to 20 meter, totally from pump centerline to tank inlet. Net positive suction head available calculation. The most critical fluid mechanics principle applied to methanol transfer is the control of vaporization and subsequent cavitation. Because methanol is a volatile liquid, its high vapor pressure must be actively managed in the section line. The available NPSH is calculated as PATM minus PV divided by density G plus Z static minus HF suction, where PATM is absolute pressure over the liquid in the surge drum equals to 101.325 kilopascal. PV equals to vapor pressure of methanol at 25 degrees Celsius, which is 12.53 kilopascal. Z static height of fluid above the pump center line 2.0 meter. Lastly, HF suction is frictional losses in the short suction pipe section, 0.60 meter, calculated in the planning phase. The pressure difference expressed in meters of methanol is PTM divided by density G equals to 13.14 meter of methanol, PV divided by density G equals to 1.62 meter of methanol. The NPSH equals to 13.14 meter minus 1.62 meter plus 2.0 meter minus 0.60 meter equals to 12.92 meter. The substantial calculated NPSH of 12.92 meter confirms that placing the pump 2 meter below the minimal liquid level of the surge drum provides a massive safety margin. This approach prioritizes static head over pressure head in the suction calculation, effectively mitigating the risk of captivation despite methanol's intrinsic volatility. For highly hazardous and volatile fluids, maintaining a large margin between NPSH and the required head NPSH is a critical safety parameter. Estimation of total dynamic head (TDH) required for a pump. The required head delivered by the pump is calculated by summing the static lift and the total friction head loss. TDH equals to Z2 minus Z1 plus HL total equals to 20.0 meter plus 14.74 meter equals to 34.74 meter. Calculation of required hydraulic and brake horsepower. The pump must supply 34.74 meter of head to move 0.0171 meter cube per second of methanol. Hydraulic power. The energy imparted to the fluid is calculated as P hydraulic Q times density times G times with TDH equals to 0.01471 meter cube per second times with 786.6 kilogram per meter cube times with 9.81 meter per second square times with 34.74 meter equals to 3,948 watts equals to 3.95 kilowatts. Brake horsepower BHP. Brake horsepower, the mechanical input power required is calculated by dividing the hydraulic power by the assumed pump efficiency. Pump efficiency. A typical centrifugal pump efficiency of 70%, which is 0.70, is assumed for this chemical service. BHP equals to P hydraulic divided by pump efficiency equals to 3.95 kilowatts divided by 0.70 equals to 5.64 kilowatts. Selection justification for pump type and efficiency. The pump required is a low to medium power unit, 5.64 kilowatts or approximately 7.57 horsepower, designed for continuous liquid chemical service. Pump type selection. A centrifugal pump is a standard choice for high-volume liquid transfer applications. However, given that methanol is a toxic, flammable, and hazardous liquid, the design specification must prioritize containment and safety over marginal efficiency gains. Therefore, a sealess magnetic drive (MagDrive) centrifugal pump is selected. Justification: MagDrive pumps use a magnetic coupling to drive the impeller, eliminating the need for dynamic mechanical seals. Mechanical seals are the most common source for leakage and failure in conventional pumps, particularly when handling volatile or hazardous fluids. The sealess design prevents the release of toxic methanol vapor into the environment, significantly enhancing reliability, uptime, and safety compliance, while MagDrive pumps may experience minor ID losses, potentially leading to slight efficiency reduction compared to sealed equivalents. The paramount requirement for zero leakage in methanol service makes the safety benefits outweigh the slight energy trade-off. Inventory policy and capacity determination. The capacity of the final storage tank is determined by operational requirements, logistics, and inventory policy. For a major industrial chemical facility, a standard inventory buffer is typically maintained to absorb fluctuations in production, delays in shipping, or scheduled plant maintenance. Consumption. Inventory period. A minimum inventory period of 7 days of continuous production is selected to ensure logistical flexibility. Based on the 1000 MTPD capacity, mass store equals to 1000 MT per day times 7 days equals to 7000 MT. Using the density equals to 786.6 kg per meter cube, the required minimum working volume is the required equals to 7 million kg per 786.6 kg per meter cube divided equals to 8899 meter cube. Volumetric capacity conversion and selection of design volume. The design volume must accommodate the required working volume plus a safety margin freeboard, typically 10 to 15%, to prevent overfilling and manage vapor space. On nominal design volume of 10,000 meter cube is selected. Storage tank design codes and material selection. Storage tanks for bulk quantities of flammable liquids like methanol are subject to stringent safety and engineering standards. Regulatory compliance and codes. The design, fabrication, and construction of large, above-ground atmospheric storage tanks must adhere to API Standard 650. Additionally, compliance with NFPA 30, Flammable and Combustible Liquids Code, is essential, particularly for managing fire protection and siting. Material selection. Since methanol has a low flash point, which is 12 degrees Celsius, only steel or high alloy tanks are permitted. Carbon steel with specialized internal coatings is common, but given the critical nature of pure methanol storage, enhanced structural integrity and corrosion protection are necessary. API 650 tanks are typically constructed of carbon steel or, for superior chemical compatibility, stainless steel 316. The design must also explicitly incorporate cathodic protection measures and regular inspections, as methanol's properties increase the risk of galvanic corrosion. Furthermore, due to methanol's wide upper flammability limit, 36 vol%, the design must include robust intake vapor control and fire suppression systems. Determination of tank dimensions based on the target design volume of the design equals to 10,000 meter cube. Standard API tank geometries are reviewed. Large API tanks generally feature diameter to height ratios that optimize shell strength and footprint. The relationship between volume V, diameter D, and height is V equals to pi over 4 D square height. For V design, 9,817 meter cube, approximating 10,000 meter cube. The selected design diameter is 25 meter, while the selected design height is 20 meter. This ratio results in a practical design that adheres to typical API 650 guidelines for large tank construction, which specifies minimum plate thickness based on diameter. The actual volume achieved with these dimensions is 9,870 meter cube, which satisfies the 8,899 meter cube required capacity plus sufficient freeboard. This table shows the methanol storage tank design summary. For production capacity, the value is 1000 MTPD for the design basis. Inventory days is 7 days. Justification standard logistical buffer. Required capacity for mass 7 million kilogram calculated from capacity and inventory. The required volume is 8,899 meter cube based on density, which is 786.6 kilogram per meter cube. The design volume is 9,870 meter cube. includes safety margin of reward. Construction standard is API standard 650. Justification flammable liquid atmospheric storage. The design diameter is 25 meter based on the standard API sizing, and the design height is 20 meter based on the standard API sizing.
Finally, I'm gonna give the conclusion. This work designs a methanol plant using carbon dioxide and hydrogen. The gases are compressed, heated to 300 degrees, and reacted at 76 bars to form methanol and water. Products are cooled, purified, and aerated gases recycled. The piping system, built with stainless steel 360 and a sealess magnetic drive pump, ensures safe, efficient methanol transfer while meeting API 605 and NFPA 30 standard. And these are our references.
And these are the appendices that we use for our calculations. Thanks for watching.